Nearly 13,000 feet below the surface, the Titanic remains exactly where it fell in 1912, surrounded by absolute darkness and crushing pressure. Before any recovery can even be considered, scientists must understand what truly remains of the ship after more than a century on the ocean floor. Modern missions rely on remotely operated vehicles to reach depths no human diver ever could, with every movement carefully calculated to avoid further weakening the structure. On the surface, dynamically positioned ships hold steady against wind and waves, creating the invisible balance that makes the mission possible. The first goal is not to move the Titanic, but to turn it into precise, measurable data. Subscribe to the channel to continue exploring the hidden mysteries of the Titanic and the engineering behind these missions. On the surface, everything depends on ships equipped with dynamic positioning systems, capable of holding their position within just a few feet. Any drift caused by wind or currents can compromise work happening nearly 4 miles below. On deck, teams prepare submersible vehicles built to withstand extreme pressure and operate for long periods without direct human intervention. Every cable, connector, and lift point is checked, and checked again, before launch. The success of the mission begins here, long before the Titanic reappears on screen. The moment the ROV enters the water, all attention shifts to the depths below. With the vehicle stabilized on the seafloor, the most delicate phase begins, the Titanic's initial mapping. Sonar sensors and photogrammetry systems record every visible surface, transforming the wreck into a highly accurate 3D model. These datasets reveal fragile structural zones, collapsed areas, and regions where any physical contact is strictly forbidden. The debris field surrounding the hull tells the story of how the ship broke apart on its descent. Each recorded fragment helps reconstruct the sequence of events from the night the world changed in 1912. Before any recovery attempt, the Titanic must be fully understood as an underwater archaeological site. With the initial mapping complete, the data are merged into a full digital twin of the Titanic. Every image, sonar scan, and structural measurement is combined to represent the ship as it exists today, not as it was built. The model reveals cracks, collapsed zones, and areas where any mechanical stress would be catastrophic. Only through this level of understanding can the recovery move forward. With the digital twin finalized, the team begins testing stress and deformation scenarios. Simulations show how the hull would respond to vibration, partial lifting, and shifts in support. Critical zones are ranked by structural risk, defining where the cradle may touch and where contact is forbidden. Every decision now lowers the odds of collapse during recovery. Once critical points are defined, construction begins on the modular cradle that will support the Titanic. Each module is engineered to distribute the hull's weight evenly, avoiding concentrated stress on weakened areas. Rails, anchors, and locking points are designed to function as a single continuous structure. Before descending, every component is tested repeatedly at the surface. With the first modules in position, the cradle's descent continues, slowly and in perfect synchronization. Each segment must align precisely with the seafloor's contours and the hull's deformations. Anchors are installed to prevent any movement caused by deep-sea currents. Stability is mandatory before any direct contact with the Titanic is allowed. Once the cradle is stable, controlled removal of sediment beneath the hull begins. The operation avoids direct jets that could damage already weakened structures. Low-pressure suction systems clear pathways for the cradle's advance. Every inch cleared reveals parts of the ship unseen since the sinking. As cleaning progresses, pathways beneath the hull begin to connect. The team confirms the cradle can slide without touching fragile areas. Minor adjustments to the seabed ensure uniform support during future movement. This stage determines whether the ship can be supported without new deformation. With pathways cleared, direct stabilization of the hull begins. Structural mats are applied to reinforce areas weakened by corrosion and impact. Containment nets prevent loose fragments from breaking away during movement. The goal isn't restoration, but ensuring the ship can bear its own weight when moved. As structural consolidation advances, real-time sensors activate across the hull. They track stress, micro-deformations, and unexpected movement. These readings determine whether the Titanic can be safely lifted. If this kind of engineering and preservation fascinates you, subscribe and follow the project to the end of this video. With all systems live, the first load tests begin. The cradle lifts the hull by mere millimeters to observe how it responds to its own weight. Sensors capture nearly invisible changes, analyzed instantly at the surface. At this stage, any unexpected response can halt the operation immediately. Even with minimal lift, the hull begins to react. Old steel plates vibrate under tension, and weakened rivets fail after decades of corrosion. Small fragments break loose and fall back to the seafloor. These signs warn that the structural limit is near and adjustments are urgent. Faced with early deformation, the team stops the lift and redistributes the load. Redundant cables engage to relieve overstressed areas. The cradle is adjusted to shift weight toward more stable structures. Each correction prevents localized damage from becoming irreversible failure. As the hull stabilizes below, conditions change above. Forecasts show a developing weather system in the North Atlantic. The team must choose between waiting for ideal conditions or continuing in controlled stages. Time now becomes as critical as the ship itself. With the decision made, the primary lift begins. Computer-controlled winches operate in perfect synchronization, distributing load across dozens of independent points. Controlled buoyancy modules reduce effective weight, allowing the Titanic to rise just inches per cycle. Every movement is slow and deliberate. Uneven lift could twist the fragile hull beyond recovery. As the ascent continues, buoyancy modules assume more of the load. Lift forces are adjusted in real time to compensate for weight shifts and asymmetry. Each rise is followed by a technical pause, allowing internal stresses to settle. The Titanic isn't lifted as a single mass. It's guided upward in a state of constant instability. After every lift cycle, operations pause for inspection. ROVs scan the hull for new cracks, compression zones, and progressive deformation. Areas once stable on the seabed now behave differently under suspension. These pauses decide whether the mission continues or stops for correction. As the Titanic rises, surface conditions grow unpredictable. Larger waves and shifting winds increase strain on winches and support cables. Dynamic compensation systems work non-stop to counter the ocean's motion. Even so, mechanical fatigue becomes a real threat, demanding constant monitoring to avoid cascading failure. Mid-ascent, sensors detect an unexpected misalignment in one cradle module. The shift is small, but enough to alter load distribution across the hull. Precision thrusters and mechanical locks engage to correct position without stopping the lift. At this stage, the margin for error is razor thin, and every second matters. With the cradle corrected, the operation enters its decisive phase. The final ascent brings the Titanic to depths with lower pressure and greater control. Lifts continue in long cycles, punctuated by stabilization stops. Once a safe depth is reached, the goal shifts from lifting to maintaining balance for slow transport to the next stage. After the long ascent, the Titanic is not exposed to open air. Instead, it's guided into a controlled wet dock, remaining fully submerged. Water temperature, salinity, and circulation are carefully regulated to prevent shock. Though recovered from the deep, the ship cannot be dried without severe risk of collapse. With the Titanic stabilized in the wet dock, a process lasting years begins. Desalination occurs slowly, reducing salts embedded in the steel. At the same time, controlled chemical agents slow ongoing corrosion. Any attempt to accelerate this phase could trigger cracking, delamination, and irreversible damage to the historic material. While the physical hull remains stabilized, reconstruction advances first in the digital world. Artificial intelligence analyzes millions of images, measurements, and historical records. Loose parts are cataloged, deformations corrected virtually, and original fits tested. Before any physical intervention, the Titanic exists whole again, digitally, guiding every future decision. With the digital reconstruction validated, the most delicate physical phase begins. Internal support structures are installed to redistribute loads and prevent progressive collapse. These reinforcements are not hidden. They remain visible and identifiable. The goal isn't to return the Titanic to 1912, but to let it exist, stable and understandable, in the present. With the hull structurally supported, preserved sections are brought together. Where original material no longer exists or cannot endure, clearly marked replicas are introduced. Every joint follows the validated digital model, ensuring proper alignment and historical clarity. The result isn't illusion, but an honest assembly showing what is original and what was recreated for stability. In the end, the Titanic does not return to the sea or to the past. It remains stabilized in a controlled environment, accessible only for technical and museum study. Every preservation choice is documented and compared to the digital twin that guided the project. The ship now stands as historical evidence, not an attraction, but a monument to the limits of human engineering, collective memory, and the lives lost.